This is the fourth in a series of resources that consider the four different types of sequences. Part 1 defines sequences and also considers sequences defined by a general rule. Part 2 inspects arithmetic sequences, the general idea, how to find specific terms in the sequence, and how to find a partial sum of the sequence. Part 3 looks at geometric sequences, the general idea, how to find specific terms in the sequence, how to find a partial sum of the sequence, and also how to find the finite sum of an infinite series. Part 4 considers recursive sequences. We look at the basic rules and formulas, then work through examples of each. The final form of sequence is a recursive sequence. In these sequences, each term is defined by the previous term or terms. Depending on how many terms are used to define future terms, we need to have that many initial terms. So while we only needed one initial term for arithmetic and geometric sequences, we may need two or more initial terms for recursive sequences. Unfortunately, there are no nice formulas to find a general term of a recursive sequence. We must work all the way to find any required term. The most famous recursive sequence is the Fibonacci sequence, which is 1, 1, 2, 3, 5, 8, 13, and so on. Formally, it is defined as a sub 1 equals 1, a sub 2 equals 1, and a sub n equals a sub n minus 1 plus a sub n minus 2 for any n greater than 2. While the Fibonacci sequence is some nice mathematics and easily defined, why is it important? The short answer is that the pattern of the sequence appears very frequently in nature. Whether it is the seeds of a pine cone, the leaves on a fern, the lengths of the chambers for a nautilus shell, or even the ratio of a number of lengths in the human body, it all boils down to the Fibonacci sequence. Suppose we want to find the next four terms of a variant of the Fibonacci sequence, the Fibonacci. It has the same definition for the terms, but it starts with 2 and 5 instead of 1 and 1. The third term is the sum of the first two terms. We add together 2 and 5, and the third term is 7. The fourth term is the total of the previous two. We add 7 plus 5 and get a fourth term of 12. We add 12 plus 7 to find that a sub 5 is 19. The sixth term is the sum of 19 and 12, 31. Not all recursive sequences require multiple starting amounts. Suppose we have a sequence that starts with 3 and is defined recursively as a sub n equals 2 multiplied by a sub n minus 1, the previous term, plus 5. We want to find the next four terms of the sequence. To find the second term of the sequence, we multiply 2 by the first term of 3, then add 5. This leaves us a sub 2 equal to 11. A sub 3 is then 2 multiplied by 11 plus 5, which is 27. A sub 4 has 2 times 27 plus 5 equal to 59, and a sub 5 is 2 multiplied by 59 plus 5 equaling 123. Now that we have seen all 4 types of sequences over the past 4 resources, let's recap. In a general sequence, each term is defined by a function rule acting on the number of the term. Arithmetic sequences add a given amount to obtain the next term, while geometric sequences multiply by a given amount. Finally, recursive sequences use a function rule involving previous terms to get the next number in the list.